In this video, I'm doing some notes on how you go about graphing polynomial functions. And so remember how polynomials can be written using this notation? It looks overly complicated though. It's really just saying that f of x equals something like, 3x to the fifth minus 4x to the third plus 2x squared minus x plus 5, something like that, okay? And it turns out that the first term and the last term, they give you information about what to expect with your graph and all, but these in the middle we don't really need for anything, okay? And notice that, the exponents, they have to be positive integers or 0. Like here at the end, that 5, that's really x to the 0 power. This is really x to the first. But the exponents in a polynomial have to be positive integers. They can't be negative. If they were negative, if you had x to the negative 3 in there, it would really be a rational function. They can't be fractional either. If you had fractions in there, they would be radicals. So to be a polynomial, you have to be you have to have exponents that are positive integers. They could be 0, but that wouldn't be written because that's equal to 1. And so you wind up with just a 5. Right, so that first term, which winds up telling us some things, is called the leading term. And then the term at the end is called the constant term. And they're the only two that really matter. They tell us a whole lot of stuff, okay? All right, so let's see what it is that they tell us. Let me get a red pen, make sure I'm in red, okay. So the n, and you see where it is, it's the highest exponent. So like up on this example, it would be the 5. N is the degree of the polynomial. We already know that that tells us how many solutions or zeros to expect. All right, so whatever n is, there are exactly n zeros. They could be real or they could be imaginary. So I'm talking about both of them. And if there are repeated zeros, you need to count the repeated ones in order for this to be true, okay? All right, and then the graph, it turns out, the zeros correspond to the x-intercepts. So you'll have at most n x-intercepts. You don't have exactly that many because only the real ones correspond to x-intercepts. The imaginary ones can't be graphed in a real number coordinate plane. Okay, and then if the degree is 3, you'll have 2 turning points. If the degree is 2, you'll have 1 turning point. So n minus 1 tells you how many turning points to expect. And that can help you make sure you have the complete graph. Okay? All right, now a sub 0, or sometimes a naught, they call it, that is the constant term, or just the constant. Okay, and if you go back and you look, it's the only term that doesn't have an x on it. And so if you wind up plugging 0 in for all of the x's, the only thing left would be that. If you plug in a 0 for all of these x's, all of those x terms with x's in them would be gone, and all you'd have left is the a sub naught. So that a naught winds up giving you the y-intercept of the graph of your function, just at a glance, okay? And you already knew that when you looked at linear. We just didn't call it a naught, we called it b, that's the y-intercept. You also already knew that with a quadratic. That's your y-intercept, okay? Now, a sub n, x to the end, that's the leading term. And it tells you a bunch of stuff, okay? One of the things it can tell you is what the end behavior of the graph should be. So the end behavior of the graph can be determined by considering the leading term. Okay, so when you think about your polynomial, remember how it was a sub n x to the n, and then you have another coefficient with 1 less degree, and then another coefficient with 1 less degree on down. So these have less x's being multiplied together. So if you put in a really big positive x or a really big negative x, the graph, and let me use function notation, the graph of f of x equaling that, if you put in big enough x's, these are small compared to this. So the graph of y equals f of x behaves like the graph of y equals the leading term. It basically determines, it overpowers. I like to think of it like that it overpowers all the rest of the problem, okay? And so like if the leading term is y equals 3x squared, I know it would look like this, okay? Ultimately, at the ends, it would have that basic end behavior. It would point up at the ends. And, you know, if it were y equals negative x, it would, at the ends, do something like that. Okay, we're going to work through some problems that get into that soon enough. I just want to get all the notes done initially. Okay, now, end behavior. Now, this looks really complicated, and it is. It does require quite a bit of critical thinking, but you just need to have that sheet there in front of you when you're trying to think about it. Okay, so the end behavior of your whole entire polynomial will be the same as the end behavior of the what y equals the leading term looks like, okay? So if you wind up having a positive x to an even power, okay, like y equals 1x squared, or, you know, y equals 3x to the fourth, something like that. If that's what if the leading term was 3x to the fourth or 1x squared, where the exponent was even and the number out in front was a positive number, okay, then both ends are going to be up, just like an x squared graph would be. And really, that's all you need to know. But you do sometimes see this notation in calculus, and I just wanted to introduce it. So as x goes towards positive infinity, the left side goes towards positive infinity. It points up. As you go to the right, as x moves to positive infinity, so as you move to the right, the y values approach positive infinity. They go towards positive infinity. So I just want to expose you to that notation. So this box was even and positive out in front, even exponent, positive out in front. So if it's positive x to an odd, that would be like y equals x, or y equals 3x to the fifth, or something like that. So you think about what y equals x does. It's just a line that looks like that. So the left end is down and the right end is up, okay? As x goes towards negative infinity, the f of x goes down towards negative infinity. As x goes to positive infinity, f of x goes towards positive infinity, goes up, okay? All right, now let's move down to this one. What's changing here is now the coefficient is negative. Okay, so pay attention to the exponent being odd or even and the coefficient being positive or negative. So y equals negative x squared. So, even when it's something like negative 7x to the sixth, it's going to behave basically like a y equals negative x squared. You know that has both ends down. When you have your x's going to the left, to negative infinity, the f of x also goes to negative infinity. It points down. Positive direction, same thing, okay? Right, and then if your leading term is negative out in front and x to an odd power, remember that's like x to the first, it's going to behave like a negative 5x to the third, negative x to the first. It's going to be something with basically a negative slope. It's going to be decreasing. It might do more like that, but it's going to be decreasing overall. So the left end is actually up and the right end is down. So when you go to negative infinity, f of x points up. When you go to positive infinity, f of x points down. See how here they're the same. Here, they're opposites. Okay, so basically for me, I think this way, and you might do better if you think x to the third, so you're thinking that versus negative x to the third, which would be that. You can also think that way. And then there might be other things going on in the middle, like that's just the end behavior. So the end behavior might be like that, but here in the middle, you might have a whole lot of turning going on. Okay. All right, now let's consider this word multiplicity and what it's talking. Oh, I hate it when it moves. Okay, good. All right, so let's talk about multiplicity. Multiplicity, I love this. Okay, this first part right here, this is the end behavior. What happens after all the turning stops? Does it go both up, or does it have one up and one down? End behavior is what happens at the ends after all the turning stops, okay? Now, multiplicity, that's really the behavior at the x-intercepts, like right there on the x-axis, right close to where the x-intercept is. Do it again. Okay. All right, let me just clean that up just a tad. Okay, so it's the behavior at the x-intercept. So this is going to be kind of fun when we do it. All right, the multiplicity is really the number of times the zero occurs, and it determines the behavior of the graph at that zero or at that x-intercept, okay? That's what it does. I don't really need that. I've already stated that, okay? All right, so the way to think about it, multiplicity has to do with the exponents on the factors. Exponents on the factors. So if you have an odd exponent on a factor, like a 1, then it's going to pass through on the x-intercept. It's going to pass through just like a line would. So like if you have a factor x minus 3 and it's just to the first power, so you have something like that, then you know at 3, it's going to go through smoothly like a line. You don't know whether it's going up or going down. You just know it's going to go through like a line would, okay? All right, if the factor, if you have like y equals x minus 3 and it's to the second power, then at 3, what you know is the behavior, the graph is going to wind up bouncing at 3, touching and turning, they sometimes say. And it might come from below and hit the 3, or it might be from the top and hit the 3, okay? And so it bounces just like y equals x squared, okay? And remember how x minus 3 would correspond to an x-intercept of 3. All right, now, if it's got an exponent that's odd, but that's bigger than 1, like x minus 3 to the 5th or something like that, then it's going to flatten. And it might flatten like, oops, that's not really that good. Let me try that again. It's hard to do these. Okay, here's 3. So as you come in from above, it flattens as it passes through that spot. If you have an exponent of 3, 5, or 7, it's going to have that look. See how it kind of looks like a cubic? Okay. But you don't know whether it's going to do it on the way up or on the way down until you get more information. All right, and then exponents of 4, 6, or 8, you really can't see the difference between those and an odd exponent unless you have them on the same graph. But it just means if you were there at 3, coming up to an x-intercept at 3, if you had a 4 on the factor, then you would just be a little flatter than you would if you were x squared. And it might be from above, or it might be doing that from below, but it would flatten more than it does here. You really can't tell those two apart. You can't tell the difference. Okay. Really. between those. And you can't tell the difference between 3s, 5s, and 7s, but you can tell the difference between 1 and the others, because 1 just goes through like a line, 3, 5, or 7 flatten a little bit like a cubic would, okay? All right, so those are the notes on it. And in this same video, I want to do one example. So let me get to the whiteboard, which is here. And let's look at one example of how you would graph taking advantage of all of this information, okay? So let's suppose you're trying to graph. Here's the example I want to do. Let me get a new one for you. What if you want to graph the function f of x equals negative 3x times x minus 2 to the third times x plus 5 squared. Okay, this right here is in factored form, which is awesome. Gives me a lot of information at a glance without me having to do very much work. Okay, so kind of the strategy you should do. First, you should have the notes filled in and printed. And the first thing you should do is you should think about the zeros of the function, because they correspond to the x-intercepts of the graph, okay? And you get them from the factors. So like x plus 5 corresponds to an x-intercept or a 0 of negative 5. Here, you'd have a 0 of 2, and then the x right there is really 0, okay? So those are your zeros of the function. Those turn out to be x-intercepts of the graph, since they're all going to be real numbers, okay? So that's the first thing you do. So the zeros correspond to x-intercepts. So what that helps you to know at this point, let me get a better picture here. What that helps you to know at this point is that you know this function is going to cross the x-axis at 2, at negative 5, and at 0. So you can go ahead and put those on there, okay? The next thing I like to look at is the multiplicity. And remember, that's the exponents on the factor that gave you the 0. And what it corresponds to on the graph is the behavior at the x-intercepts, or at the zeros. That's what it tells me. So do you see how the 0 had an exponent of 1, x minus 2 had an exponent of 3, and x plus 5 had an exponent of 2? Then you would say that 0 is a 0 of multiplicity 1, or you don't even say it has one, okay? 2 has multiplicity 3, and negative 5 corresponds to x plus 5, and so negative 5 is a 0 of multiplicity, we'd say, 2, okay? So what you should think at that point is that this one's going to behave like a line. This is going to behave like a cubic. And this one's going to behave like a parabola. Okay, because the exponent was to the first, to the third, to the second. So like a line, like a cubic, like a parabola. All right, so that helps. I can't quite use it quite yet, but I will in just a second. All right, the third thing, okay, so that's multiplicity. Okay, then the third thing I want to look at, or that I consider, is end behavior. There's only 4 things that can happen. It's either going to both be up, both be down, or one up, one down, but I don't know which direction, right? So I've got to figure out which direction, okay? So I've only got 4 choices, all right? So the end behavior, that corresponds, that has to do with the leading term. Okay, and when something is in factored form, I really love it for these 2 things. But when I'm trying to do the end behavior, it kind of hides. The leading term is a little bit hidden because it's in factored form. It's not all multiplied out. Okay. So when you're trying to figure out the leading term, what you want to do is you want to think about, if I were to multiply this out, this is x plus 5 twice, this is x minus 2 3 times, this is minus 3x once. What would happen if you were to take the x plus 5 times itself and FOIL it all out? Only don't do it all. All you care about is what the first part of this turns out to be. So when you have negative 3x to the first, and then x to the third, and then x to the second. So if you were to multiply it all out, you'd have negative 3x to the 1, 2, 3, 4, 5, 6 to the 6th power. And then you'd have, plus a bunch of other stuff that we don't care about right now. Okay, so the leading term is what matters. And the leading term on this turns out to be negative 3x to the 6th. Okay, and so the whole entire polynomial would behave at the ends like y equals negative 3x to the 6th. And that, in more simple terms, is going to behave like y equals a negative x to an even power, so like a parabola. That's kind of the thought process I go through. Okay, so let me squeeze this in just a tad so we can get the graph done now. All right, so after I do those three things, here's what I think. Ultimately, both ends have to be down. So start at the leftmost side, okay? Let me do this in black. So I'm getting ready to graph. So I'm going to start graphing. So I'm going to approach the x-axis from below, and this is the negative 5, okay? And negative 5 has an exponent of 2, and we already decided it should behave like a parabola. So as it hits the negative 5, it needs to touch and turn or bounce right there, so it looks like a parabola. Now, it's going to have to turn around so that it can hit 0. So I'm going to get ready to do that. And when I get close to 0, I got to think about how it should behave there. So I go and I look, if I haven't already, at the exponent on the factor associated with that x-intercept. See how it's to the first power? See how it has multiplicity 1? So it's going to have to go through smoothly there. Okay, now it's got to hit 2. So it's got to turn around at some point. So notice my y-axis doesn't claim how high up or down things are. Okay, so I'm going to go up a little bit. I'm going to turn around. And when I go through 2, the exponent on it is a 3. It had multiplicity 3. So it has to behave like a cubic. So it has to flatten a little bit. So as I turn around there, I need to flatten as I go through. So it's like you get a little mini cubic, a little mini line, here a little mini parabola. But overall, it looks like that. And that is how you graph a polynomial that's in factored form. Okay. All right, so let me stop this video and we'll do some more examples that are in the homework.